I made it, barely, but sorry about the little delay. Good thing we didn't have a quiz today. I want to warn you that we're covering sections 10.1 and 10.2 today, which are actually really straightforward. The warning is that 10.1 is all about what's called linear correlation, and 10.2 is all about regression, but they're directly tied to each other. And so the first example in 10.1 also happens to be the first example in 10.2. So I'm going to have you flipping back and forth from one section to the next, because we're going to kind of do them simultaneously, even though they're in our packets. They're on separate pages. They start on page 144. We start on page 144. But if you want to make a little note or a little tab, we're going to be flipping back and forth. We're going to be flipping over to 148. Or from 144 to 148 and back as we go, but I will warn you when we do that. So we're starting at 144. And the really good news is we only have 2.5 more days of lecture. Yay, little celebration there. Today we're doing all of chapter 10, which is just these two sections. When I see you on Wednesday, we're doing the two sections that we're covering in chapter 11. And then next week there's just half a day where we're going to talk about, we won't even need half a day, probably 20 minutes at most, half hour, to talk about the one section in chapter 12. Questions? The test is November 29th, a week from Wednesday.
And then what are we doing?
The projects are on December 4th. We're actually going to talk about part 2 of the project, do the second half today. Probably the last 20 minutes or so. Other comments or questions? Okay, are we on 144? So 144 talks about a correlation, and it's looking for some relationship between two quantitative variables, some x and some y. Like maybe there's a relationship between the number of pets you have and the amount of money in your wallet right now. I doubt it, but maybe there is a relationship. Or there's definitely a relationship in general on people's heights versus their shoe sizes. It tends on general that people who are taller have bigger feet. Not always true, but in general it's kind of a trend. So we're looking for that relationship. And the way we can visualize it is with a scatter plot. We made scatter plots back in August, it was a while ago. The 3 pictures I have at the top of the page here, those are all examples of scatter plots, where you plot the XY points like you learned back in algebra. So for example, the first one is about the size in carats, probably of diamonds, I would say, and the prices. So there's a little dot where you find the size, you find the price, put a dot there, and so forth. The other ones aren't really labeled, so we don't know what they're measuring. Remember scatter plots from before? We're going to create a couple today. So what we're looking for is looking to see which one of these, or if any of them, show a linear relationship, a line that kind of goes through the data points. Which of these looks most like a line? The first one for sure, right? You can practically draw the line right through there, see where it would go. How about the second one? The second one look like it has a line through it? A little bit, she says. Is that line going up or down?
Down.
Yeah, you can kind of put a line through there, starting from the top and kind of going down towards the right-hand corner. It's not a real strong line. I mean, it's not like they're definitely lined up, but you can at least see where the trend would be. And what about that last one? No, I mean, which way would you draw the line? I don't even know where to guess either. So we talk about the first one being a strong correlation, the middle one being a weak correlation, and the last one having no correlation. So how close it is to a line is how much correlation it has, how strong it is. And we use the letter R, which is right underneath those pictures, to be the linear correlation coefficient. And there's a little description of R in the middle of the page there. R is always a number between -1 and 1. It can't go past those. If R is 1, then your data points are in a perfectly straight line that goes up. So kind of like that first one, if they were perfectly straight, R would be exactly 1. And if the second one was perfectly straight, which definitely it's not, going down, then it would be negative 1. So the sign just tells you if it goes up or down. And how close it is to 1 is how close it is to a perfect line. And guess what 0 is? No correlation, which would be probably what we have on that last picture, right? There's no correlation, so R will be really close to 0, if not 0 in that case. So what I want to do is just estimating with those 3 pictures. I'm going to call them A, B, and C. The 3 pictures. What kind of number might you assign, if you had to guess, what kind of R would you put with any one of these? There could be 3 different R's. We just talked about this one. The third one? Third one would be 0. There's no correlation that we can see there. How about the first one?
1.
Is it exactly a perfect straight line?
No.
So it can't be exactly 1. So
0.9.
she's close. 0.9, is that what you said?
Yeah.
Yeah, so something close to 1, but not exactly 1. I like 0.9. It's kind of like probabilities, right? Where the closer you are to 1, the closer it is to be guaranteed. You can't tell by looking what the number actually is. So if you had said, I think it's 0.8, I wouldn't have argued with you. But it's closer to a straight line than not. So it's something, closer to 1 than 0. What do you think you might put for B?
0.5?
0.5?
Negative.
Negative 0.5, she's corrected that. You see why it has to be negative? Negative because it's going down. It might be slightly lower or higher than 0.5, we can't tell by looking. But the thing you're looking for is the closer the number is to 1, the closer it is to a perfect straight line. And the farther from 1, the more likely is there's no line there at all. You okay on what we're looking for there? Okay, so let's start the first example by drawing a scatter plot. So example 1a asks us to construct that scatter plot. 1a. And they give us all of these xy pairs. They don't really tell us what they represent. And they want us to put them on our graph. I gave you a piece of graph paper on your notes. What should I count by for my x's? What do my x values go from? Maybe count by 1s, because we have to go up as high as, what's the highest x? 14 is the highest x, so maybe we count by 2s. You guys could probably count by 1s on yours, but I can't quite fit that up here. So maybe I'll count by 2s. 2, 4. You could probably count by 1s on your graph paper I gave you. We just want to make sure we fit all of the x values that go up to 14. If they went up to 140, maybe I would have counted by 20s or something. And then what about the y values? They go from, I see a 3 up to 9 point something. So maybe I'll just count by 1s for my y values. You guys might be able to go every other one on yours, I don't know. That might be going a little bit too big, we'll see. I have to extend it up a little bit. So the first thing you want to do is mark your axes to fit your x's and your y's. Now it's just algebra review, right? You think of these as pairs. The first one, 10 goes with 9.14. The first pair there. So I'm going to come over here to 10. I'm going to go up to 9.14, which is approximately here. And put a little dot there. 9.14 is a little bit above 9. See what I'm doing there? Remember this from your algebra days? And the next one is 8 and 8.14, so I come over here to 8. I'd go up a little bit past the 8, which is roughly here. So do me a favor and take a minute and try to put the rest of those in there. See if we get the right picture. Christiana? We're drawing the picture on page 144. Did you get something like this? Mine's kind of smushed together because I don't have my graph paper there. Yours is probably better, but look something like that. So that's an example of a scatter plot. We did scatter plots, like I said, back in August, which feels like forever ago. So now if I handed you this one along with those other ones we did earlier at the top of the page, and I asked you to estimate R, first off, do you think R is positive or negative?
Positive.
Positive, why?
The majority of it's going up.
Yeah, most of it's going up in general. If you kind of stepped way back, you'd see this trend going up. So I agree that it's positive, some positive number. This is our estimate. Estimate has a T before the I. There we go. What kind of number do you want to use? It's just a guess. I don't care if we're wrong. I just wasn't an educated guess. 0.95? Why do you say 0.95?
Oh, it looks like a really straight line, almost a straight line. But there is a curve, so.
So yeah, she said it looks like almost a straight line and then it kind of curves down. So what does that little extra curve do? So she wants to go as high as 0.95.
I was gonna say 7.5,
You want to say 0.75? And why do you say 0.75?
because it goes up and back down.
Yeah, because it does go up and then it goes back down. So I can agree with that too. We're actually going to be able to calculate it in a minute here to see what it actually is. Anybody have a different guess? You say 0.80, it's a little bit higher than that. These are all guesses. Notice that they're all positive because it's going up in general. And they're all more than like 0.5 because it's pretty close to a line. And so there's this whole very nice, messy, long formula on how to calculate the R, the correlation coefficient, but instead we're going to ask our calculators to do it. So over there on the right, at the bottom of page 144, down here, are the directions on how to get the R coefficient. The first thing we're going to have to do is the same thing we've been doing all semester, is to put the two lists into our list 1 and list 2, or any two lists that you want.
I think 73.
Did you already do it?
No.
Something tells me that he's psychic. I'll hold this down for a second. So type all your numbers into your list 1 and list 2.
I skipped it. It says right here is the,
Yeah. So we should have it. I got it.
oh, you got it.
Oh, that's our score.
You still did.
Every one of us was another one.
Somebody.
Something did, something else.
So we have to type them all in correctly.
We're gonna watch it.
That's the tricky part. Put them in here. Oh, I forgot, I was laying the pins down.
What did you get for Apple? Give us the scatter.
How do we know?
Just get for Apple.
Okay, you got them all typed in there?
Yeah.
And then, if you look at the directions, it says to go into stats and tests. So the same thing we've been doing with all our other tests. So I'm going to go over here to stats, come over here to tests, and it's called a linear regression t-test. We're looking for this linear regression. It's called a linear regression t-test. Short is LINREG. So I'm going to go down, it's pretty far down there. Computer's on delay here.
Oh, I think I missed a number.
Did you miss the number? So it's not 0.73, you're not psychic?
It might not be. Well, it says my degrees of freedom are 9. I think there's 11 problems.
Oh.
1, 2, 3,
Linear regression t-test?
7, 8, 9, 10, 11.
You guys probably found it faster than I did.
Yeah.
You're fixing yours now, Brian?
Yeah.
Okay, so when I hit enter, it wants to know where I put my data. So we put I put mine in list 1 and list 2, but if you put them somewhere else. The frequency is always 1, like it has been for all of our other tests. We're gonna always choose the not equal to. We'll get to that in a minute on why that is.
Mine says 9.
And then we're going to come down here to calculate and hit enter.
EQ is happy.
Just leave the REQ as blank. And you get something that looks like this. Tell me if your numbers don't match mine, so it means I typed something in wrong. Do we agree? Disagree? I got Liam nodding. Most people are nodding. So here's the bad news. If you didn't get my numbers, it seems like you made the mistake. Because without people agreeing with mine. What were we looking for? R. I don't see an R there.
Scroll down.
Yeah, see the little arrow? Tells me to keep going down. So keep going down and find the R. So I'm going to go down with my arrows. Oh look, there's R. I think Evelyn wins. 0.816. Right up here. R equals 0.816. So the first couple homework problems in this section will be create a scatter plot and find the linear correlation coefficient. That's the beginning part there. Questions on how I did that? Yes.
We have to graph it like this for the test.
For the test? The exam next week, you mean? Or on the, for the linear regression, like the test?
Well,
The hypothesis test or the exam?
The exam, like, will we have to graph it like this on there?
You might be asked to graph a scatter plot, yes. You also can do a scatter plot on your calculator, it does them as well. But I'm more concerned with whether or not there is a linear relationship than whether or not you can draw the linear relationship. Other questions? Okay, let me turn the lights back on here, and then we'll keep going. So then the question is, how high, so this is our actual R value. That's the actual R value. So this guess is a little bit too high, a little too low, so pretty darn close. You can't just tell by looking. But the idea is, well, how high is high enough to say there really is a pretty good linear relationship? Right, because close to 1, what's the definition of close to 1, right? So it's the same thing like all of the other hypothesis tests we've been doing. What's that cutoff to say, yep, that's big enough to say there's a linear relationship? A linear correlation, we call it. So again, we have two ways of doing it. We've got critical value methods and p-value methods to decide if there's a linear relationship or not. So we actually will write out an entire test to go with it, a hypothesis test. So I'm now over on page 145. Turn the page over there. used R for the linear correlation coefficient. That's for our sample that we just had. If you want to use the corresponding Greek letter that goes for the population, it's a Greek rho. You spell it R-H-O, rho. And you're not going to like the way it looks, so I'm horrible at drawing them. It kind of looks like a P, like kind of like that. It's a rho. Do I have an example of one on here? I don't. Bummer. Should have had one printed on here. I don't have one in our notes. You look at it in our section in the book, or let's see if it's on here. It might be. I want you to see what it looks like because I can't draw them very well. No, it's not here either. Bummer. I should have an example of one for you, but you'll see it when you pull it up online. It kind of looks like a P. It's actually an R. The Greeks are very different from us. Okay, so this is the linear correlation coefficient. It's important though that you not write it like a P. Like don't write it like this, because then I'll think you're talking about proportions, right? It's not a P. It looks like a P. It's kind of a script P in a way. It's actually a rho. It kind of has a weird little loop on it. So this is the coefficient for the population. And this one was just from our sample. Similar to how we had an X bar and a mu, or an S and a sigma. Is okay what I'm talking about there? So the claim is always going to be testing whether there's a correlation or not. If there's not a correlation, what will rho equal? If there's not a correlation, zero. That's what it means to not have a correlation. And since it's equal to zero, that's always going to be your H0. This means there's no correlation. Rho equals zero means there's no correlation, just like R equals zero. This needs to be underlined. I don't want to do that. So guess what H1 is? The equals with an H0. Does not equal. Which is why I had you choose that option when we did the test a minute ago. And that means there is a correlation. So either there's a correlation or there's not a correlation. Only options we have here. You technically could have a problem that says test for a positive correlation, in which case positive would be greater than zero. But almost all the time, I can think of very few exceptions, you're just asked test to see if there's a correlation or not. So it's not even clear which one's the claim. Is the claim that there's no correlation? Is the claim that there is a correlation? We're just testing to see, is there no correlation or some correlation? So that's always, every problem here, going to be your H0 and your H1. Okay. And then we have our test statistic is our R. So this is, step one of our 5-step hypothesis testing that we do. Step 2 is get your test statistic. It's your R. So our R equals 0.816. That's our test statistic. What's step 3 of our 5-step process? Anybody remember? Ooh, that's step 4. Either get the p-value or the critical values. This section will ask you to do both ways. The critical value method is actually more common. So the critical value method, it's kind of like a normal thing, but I'm not going to draw the curve. We're really trying to see what's the cutoff over here and over here, so that anything over here is close to 1 or -1. We're looking for these regions over here, kind of like the tails that we talked about. Our stars are my critical values. So when you look on your table on page 3, oh look, there's the row I couldn't find. I found it. Page 3, there's this little column on the right-hand side. I'll wait for you guys to pull out your packet. You know we're going to use them every day. I told you that. So on page 3, it says we're testing the claim. It even tells us what the claim is up there. Row equals 0, row not equal to 0. See how they make the row? It kind of looks like a P, but it's not really, kind of sideways. It's even loopier in the book. All we need to know is our degrees of freedom, excuse me, not our degrees of freedom, our sample size, which is not degrees of freedom in this case. See how it just says N? Our sample size, and we need to know our significance level. Did this problem tell me a significance level? Yeah, 0.01. Again, I forgot to write it down. But let me warn you, in this chapter, quite often they won't give you a significance level. They'll forget to tell you. So when they don't give you one, the default is 0.05. So if you're ever going, I don't know where my alpha is, I don't have a significance level, just use 0.05. As long as you tell me which one you're using, though, I can follow your work. So if we have alpha equals 0.01, and our N is our sample size, what was our sample size? There's 11 pairs there? I didn't count them. There's 11 pairs here. We go down to 11. For 0.01, I see 0.765. 735? I want to say no. Oh, 735, thank you. 735? So that is the cutoff right here, 0.735. Guess what this one is over here? Negative 0.735. Now technically, if you're doing this problem online, they're only going to ask for the positive one, because they want you to take the absolute value, but it's still the same idea. This is the one they're going to ask for online, the positive one. So any R bigger than that tells me we do have a correlation, and if it's not bigger than that, then we don't have a correlation. Where is our R? That's hard to say. Our test statistic was 0.816. So it's after 0.735, right? 0.816 is over here somewhere. Because this is kind of like the little tails that you want to be in, right? Those are like our rejection regions. Or our tails, if you wanted to think of it under a normal curve. It's not a normal curve. Similar idea. So Kirsty says, so there is a correlation. So because we're in the tails, past the critical region, now we're on our old step 4, which is reject H0. Right? Reject H0 because you're in the critical region. And the conclusion is tricky because you're like, there wasn't test the claim. It doesn't say test the claim that. A lot of you say, I'm just going to restate it. Now this one does say test that there is a linear correlation. So I guess we could say that this one is a claim. Because this one actually said it. You'll see ones coming up where they don't tell you what the claim is, and we'll talk about how to write the conclusion. So what's my conclusion?
There's sufficient evidence to support the claim.
There's sufficient evidence to support the claim of a linear correlation. So usually what we just write, though, is there's sufficient evidence to show a linear correlation. Questions on that part? No questions? What's our other option besides the critical value method? P-value method? Where do we get the p-value? What'd you say? Off our calculator. When we had that screen that gave us the 0.816 and all that other stuff, the p-value was there. Go back and look that up for me.
1002.
003?
2.
002? You guys see that on your screen still from before? It was on there. So you could also use the p-value method, which again, because this is less than 0.01, we would also reject because of that reason. So on a written exam, I don't care if you do critical value method or p-value method, but a lot of the online stuff wants to make sure you understand the critical value, so they'll be asking for those R's.
It's less steps to just use the p-value.
It is, that's why most people prefer the p-value method. In the old days though, we didn't have technology that gave us p-values, so we all had to do by hand and use critical values, so that's why like a lot of the books don't let it go. It's still an old process that we're familiar with, some of us are at least. Okay, before we move on to the next example though, I'm now going to do what I warned you about earlier. I'm going to flip over to section 10.2. Because what 10.2 does, it says if there is a line, well what is the line? And we can use it to make predictions. So if you flip over now to page 148. Page 148, we can do this flipping back and forth thing here. Let's take this out right now. Ignoring the stuff at the very top. Notice example 1A. Does it look familiar?
It's all the same
It's the
thing.
same thing. It's the same thing exactly that we just did. Construct the scatter plot. We just did that. And it even says find the regression coefficient and all that like we did. Okay, what's different now though is you can find a regression line. You can actually find what is the line that I should draw right through there. So at the top of the page now, our notes will call it, I'm going to put a note right here that now we're doing 10.2, page 148. Has this y hat equals b0 plus b1x. Looks like this. Some of you remember from your algebra life, y equals mx plus b? You had to graph an equation of a line back in algebra. That's what this is representing. This is like your mx plus b that have it out of order. Yeah, the slope and the y-intercept, we're actually going to use that in a minute to graph it. But it's finding the equation of the line. This is the notation our book uses to find the equation of a line. This is just what we used in algebra. Our calculator uses yet something even more different. But go back up to that screen. Actually, I should probably pull it back up here. The screen that had the results at the top of the page. I want to point to it while I talk about it to make sure we're clear. So after you do the linear regression t-test, before we scroll down, wait for it to warm up again. You see what it says at the very top of the screen there? Computer totally froze. Well, good thing it's still here. I can point to it. Can't move my mouse. Y equals a plus bx. See on the top of your screen there? That's the same thing that our book calls b0 plus b1x. So if you're doing an online problem and it says find the regression line b0 plus b1x, the b0 and b1 don't show up on our calculator, but our calculator shows us that it's a plus bx. And then look a little bit further down here. There's a and there's b. See how they're right there? They tell you which order to put them in, and they tell you which one's A and which one's B. Good? Yes?
That's like the supplemental, like the calculator's formula, but it means the same thing as that one?
Yes.
Y hat.
Right, I'm going to write my y hat down here in a second, as soon as I'm done pointing at this. But yeah, so the notation changes based on your book versus your calculator, but the same thing. You will be asked to find the equation of the regression line. And so this tells me to plug 3 in right here and plug 0.5 in right there. A is, it's part of the line. It's called the y-intercept when we go to graph it. We'll do that in a second. A and B are just the two numbers that go in the line. I'm about to put that in there and show you what to do with it. Everyone clear where I'm looking at A and B on here though? Turn it back off one more time and then my computer decides to unfreeze. That's weird. Doesn't want to go all the way up. Technology. So you guys all have those numbers in front of you. So our calculator calls it y equals a plus bx. This is the calculator notation. This is our book's notation and our notes. But no matter what, the directions are find the equation of the regression line. So based on the a and the b that we just saw there, our equation is y equals 3 plus 0.5x. Because a was 3 and b was 0.5. This right here is the regression line. Now here's an algebra review question for you. How do I graph that?
3 is the y,
3 is the y-intercept.
and then there's a 0.5 is how many,
She remembers part of it.
you
3 is
go
the
up and
y-intercept.
over, so.
Uh-huh.
Oh, I know.
Good, she totally remembers it. So Evelyn mentioned before, this is the slope. The slope is 0.5, so you go up 0.5 and over how far?
Wait, no.
Three. Up,
No,
three,
that's-
over, 0.5.
3 goes
The
up,
slope is 0.5. That's your slope.
over
So-
1,
So you could write this as 0.5 over 1,
yeah.
or you could think of it as a fraction. 0.5 is 1/2, up 1 over 2, jogging your algebra memories here. I'll show you how to get you the same thing either way. So from 3, I could go up 1/2
And then.
and over 1, which would put me about right here. Oops, I switched colors on you, sorry. I could go up 1/2 and over 1, or I could go up 1 and over 2. See how it doesn't matter, I'll get the same line when I connect the dots. And then if I carefully and accurately connect these dots with a straight line, it looks something like that. It's not very dark. Can you see that, Nick? Let me make it darker. Pretend it's a straight line. So that's the line that best fits our data. So we said, is it linear? Is there a linear relationship or not? Remember we said there is evidence of a linear correlation. So then the follow-up is, well, if there is, what's the line that best fits it? So this is the line that best fits it. So when the directions said on page 148 off to the side, it said find the regression line and graph it on the same axes. We found the line and we just graphed it on the same axes. Questions there?
Are
Yes.
we still staying on page 148?
I couldn't hear you.
Are we staying on page 148 or are we going back?
We're going back after we're done with this example here. The reason we're jumping back and forth is it's the same data for each example on each section, and it's ridiculous, in my opinion, to put it all in your calculator, do the next one, and have to go to the next page and have to put the old stuff back in again. So because they're directly tied together, we're going to be doing the jumping back and forth. So we're okay on finding the line, which is handed to you really, and graphing it. Graphing might take some review if you don't remember your algebra. Now, the bottom of the page, there's very deliberate caps and bolds down there at the bottom of page 148. If there's a linear correlation between the two variables, if there was a correlation like we found in this case, that's a really big if. If there's a correlation, we can use this line to predict y values. We can use the line to predict y values. So if I come along and say, oh, I have a number that's 8.5, what's the y going to be? We can say, oh, it's going to be whatever it would be right here on this line. We're going to assume that line's the best prediction. We're about to make a prediction in a minute. But then the next line down, if there's no correlation, like my example earlier about how many pets you have and how much money's in your wallet, I'm not going to ask you how many pets you have and plug it into an equation to estimate how much money's in your wallet, because there's no relationship there. Where if you tell me how many hours you work, I can plug it into an equation and figure out how much to pay you, because there is a relationship there. So you don't always use that equation. You can only use the equation when you do have a correlation. If there's no correlation, then the best prediction is the mean value of y. So if you said, hey Jill, guess how much money's in my wallet right now? I'd say, hang on a second, let me see what everybody has, and then I'll just take the average of those, and that'll be my best guess. I'm not gonna say, first tell me how many pets you have, because there is no relationship there. We'll go back to this, but that stuff on the bottom of page 148 is crucial, because every problem in section 10.2 asks you to get this line, but you can't always use it. You can't use it unless you have a correlation. We'll see an example coming up where there is no correlation. Questions? Example 1b. What's the best estimate for a y value corresponding to an x value of 13.5? So if I'm over here at 13.5 on my x's, we want to guess what this y value is up here on the line. How would I find it?
Just plug in 13.5.
Plug in 13.5 for x into my equation and figure out what y is. That's what this is doing. This is my line that makes the best prediction. So for 1b, my y hat, I didn't put my little hat on it. It's a hat. Doesn't really matter. I don't care if you write the hat or not, but the computer will. We're going to plug in 13.5 right here for the x. And we will get, let you guys do that,
6.75.
plus that 3, right?
Oh, 9.75.
9.75? Does that seem reasonable? If I'm at 13.5, does that look to be about 9.75? Looks like it is pretty much from my scale here. So this is my best prediction. We do not always plug the x's into the equation to get the prediction. We only plug them in when we find that there is a linear correlation, because then the line is our best prediction. If there's no linear relationship, even if your calculator can find one, it's a bad one, so we're not going to use it. Another warning is that this line only works for numbers between 0 and 14. If I came along now and says, hey, what if x was 30? I could plug 30 in here and get a number. I agree, it would work. But we don't know what this data does after this. What if it keeps going down? Then that'd be a really bad example for 30. So you don't ever want to make predictions outside of your interval because you don't really have any information about that. There's a couple in the lab where we say, what's wrong with this? And usually it says you're outside the interval.
So you only do predictions when there is a linear correlation.
See that again? We're
You
only
only do
talking to
predictions
me.
when there is a linear correlation.
Yes, you only use well, you make predictions, but you only use the line to make predictions when there's a linear correlation. Our next example will be what to do if there's not a correlation. Questions? Okay, let's do another one in a lot less time. And then we'll take our break. Let's flip back to 145 and look at example 2. Example 2, page 145. So we have concerns about global warming. There's some data here about the carbon dioxide levels and the temperatures. And it says use a 0.05 significance level to test if there's a linear correlation between temperature and carbon dioxide levels. So what am I going to do?
HO and H1.
HO and H1, which for linear correlation questions will always be
0.5.
Row.
Zero.
Row equals 0,
Row does not.
row not equal 0.
That's what I was-
That's what he meant. You were thinking, what if we don't have
Yeah.
significance level? I was with you. I like to write these words next to it. You do not have to write these words, but it helps to remember which one is which so that you'll know what your conclusion tells you. No correlation, yes, there's a correlation. We were given alpha equals 0.05. Then what?
And then you do the line T that.
Yeah, the linear regression t-test, we have to put all the data into our calculators. See if I can get my computer to unfreeze. I can, what the heck? I need to trust you guys to type those in and do the linear regression t-test. Can't even force restart it. Everyone clear what we're doing? List 1, list 2, linear regression t-test. My computer's yelling at me now as it restarts. Yes. Left or right test? Showing you where.
No, not that. The person that shows you if it's showing what the test or not.
Oh, you mean this? Where it tells you?
Yeah. Nice.
Yes. Okay, most of you got there? Did you get a test statistic? Of an R? 0.892? We agree with Evelyn's R? By the way, this test will give you a T, which looks like T is your test statistic. It's actually running a version of the t-test, a different t-test than what we've seen before. But when we're talking about correlation, the R is our test statistic. What's the critical value? Let's do that just to humor me. Not the p-value, the critical value. Critical value.
M is 10,
N is 10?
4.632.
He says 0.632.
Yeah.
She's agreeing with him. How'd they get that?
This little chart.
On this little chart on page 3, N, we had to count how many pairs of data you had. There were 10. So you go down to 10, over to 0.05, which was our significance level, and it's 0.632. So that's similar to what I did here. Anything past 0.632 or before negative 0.632 would be a correlation. You could also do the p-value, which your calculator gave you. Which was? 3 zeros? What was the last number? 0005?
Yeah.
Yep. Yes.
For that, could we put, 0 plus? And then just
include like the scientific notation?
Usually we only do 0+ if it's more than 4 decimal places, like if it didn't start till the 5th one. So if you can fit, because usually they ask you to round your p-value to 4 places, so in which case you'd have to round it to 0.005.
Okay.
I usually only use 0+ when the first 4 round to 0.
Okay, yeah, because on mine it just says 5.21 or something, and then E negative.
Yeah, so E negative 4 means you can still fit it in 4 decimal places.
Okay.
And so what's my decision?
Reject.
Reject H0. So my conclusion,
There's not a correlation between temperatures.
there's not.
Yeah.
No.
You want to guess again, Brian, before they all yell at you?
Reject H0. There is a correlation.
Thank you. Want to give you a chance to save yourself before they all started yelling. They were getting ready. We all agree that there's evidence of a correlation? Because we rejected H0, we rejected this. So we have evidence of a correlation? A lot of you asking questions of each other, which is good. I'm pausing to see if anybody has a question for me. It's the same thing, those darn conclusions. Which is why I like to write this out. By writing this up here, when you reject that there's no correlation, then the only other possibility is there is a correlation. Okay, so now flip back over to 149. Told you we were going to flip back over, but look at the example 2 on page 149. Example 2 on page 149. Exact same data, exact same scenario, but what is it asking for? Find the regression line is the first thing it asks for.
The best prediction.
And then make the best prediction. So where am I getting the regression line? Y equals A plus BX off of our calculator. And when you're doing these online, the MyStatLab will tell you where to round if they need to be rounded. A and B aren't always nice perfect numbers. What is A? You guys have your calculator screen in front of you still, where you got this one?
10.48.
10.48. So we'll round to 2 decimal places. Does it round to 48?
Yeah.
Plus
0.011.
0.11?
Yeah.
This is the A and the B from your calculator? So the first part of this question was find the regression line. There it is. I'm sorry? We just put the A in the front and the B next to the X. That's all you have to do to get there. I mean, there's no work to do once you do the linear regression t-test. So that's the creation of the line, and then the next part is to make a prediction for when the carbon dioxide is 320.
We always have to include the hat.
I don't care if you put the hat or not.
Yeah, okay.
But when you're doing it online, it'll ask you for y hat equals, and so I just want to make sure that that's the prediction line that they're using.
Okay.
What am I going to do to make the prediction?
Plug it in and.
Put the 320 in for my x. 10.48 plus 0.11 times 320. Yes?
It's a decimal on the second of it.
Oh, thank you. I got creative with my decimal. Give me a different answer for sure. What do we get?
14.
14? Exactly? Does that make sense according to this data? Does 14 seem reasonable?
Yes.
Yes, what?
Please put 14 over 1.
Because what?
Put 14 over 1. Make 1.
No, but according to this data here, how does it fit this data?
temperatures have 14.
Yeah, the temperatures that are listed are all like 13.9, 14, whatever. They're all in the 13, 14-ish range. So it makes sense that my prediction would be somewhere in there. If I had accidentally done what I did with the decimal, I would have had like a 140. And that wouldn't have made sense. Like, wait, that can't be 140. That's not anywhere near this data. So you want to look at your data and see if your prediction makes sense. We good? Yes?
That's the best way to write the answers is the y-hat for the line regression and then the y-hat underneath it for the prediction. You don't have to write like a sentence or anything.
The only sentence that we needed was to talk about whether there was or wasn't a correlation. What's interesting is the question that I just asked on page 149 for 10.2, you'll quite often just be asked the make a prediction question, which really means, oh wait, first you have to go do a test and see if there's a correlation and get that line, and now you can make the prediction. So which is why I'm doing the two sections together. Because in the one section it's just, is there a correlation, yes or no? And the second section is, can you make a prediction? And so, but they're totally tied together, which is what we're doing. We'll do a couple more of them after our break. Okay, let's take a 10-minute break. I'll give you your exams back as you come back in, or if you hang around, I'll give them to you then. And then we'll finish this and talk about our projects. We good? All right. Let's do the third example in 10.1, which then becomes in 10.2 as well. Example 3 on page 145. Example 3 on page 145, we now have brain sizes and IQ scores. Brain sizes and IQ scores, so they measured how big someone's brain is and they measured their IQ score. And we're looking to see if there's evidence to say there's a linear correlation between brain size and IQ score. It doesn't really say test the claim, right, but it implies that.
We use 0.05, right?
Yes, so this is an example where they didn't give us a significance level. So they start doing that in chapter 10. Alpha equals 0.05 if they don't give us one. That's the most common one. What are my claims?
P equals 0 or
It's not a P, it's a row. It only looks like a P. Row equals 0 and row not equals 0. If it were P, it'd be a proportion. It'd be a one prop B test, something totally different.
it's like italics P.
Okay, yeah, italics B, I'll give you that. And equals 0 means there's no correlation. And not equal to 0 means there is a correlation. And then you're going to carefully type that all into your calculators to get me my test statistic. Some are quicker than others. I'll pull up this example while you're doing that. We talked about that. If they don't give you one, we use 0.05 as the default. They warn you guys all semester long, and finally in chapter 10 is when they start forgetting to give them to you. And the reason they don't give it to you is they don't actually say test the claim, but you have to test it to decide. Yes?
So for H1, why would it be greater than?
Greater than would only be if you're testing for a positive correlation. You could have a negative correlation and still have a correlation. Because remember, positive just means it goes up, and negative means it goes down.
So since it says larger brains are more intelligent, you still just say that it's not equal to?
Yes, that's a follow-up question of something different. We could answer that once we get our R and see if it's positive and if we have a correlation. So the calculators have quieted down. Does that mean we have R? What is it? Again?
0.263.
0.263? Agreed? Is that a big or a small R? It's pretty small. It's closer to 0 than it is to 1. It's a pretty small value of R. What would my critical values be in this case? She's faster than me. What's my N? N is 12. So the critical values, she says, are 0.576. She got that off of the table on page 3? In terms of a picture? Anything in here would be closer to 1 or negative 1 to tell me I do have a correlation. But what do I have? 0.263, which is between 0 and 0.576. It's over here, not past that cutoff. So it's not big enough. It's not a big enough correlation number. It's not 0, but it's not close enough to 1 to be a linear correlation. What was your p-value? 409? Clearly not less than alpha. Right, that's definitely greater than alpha. So either case tells you to fail to reject H0. The first one we've seen where we failed to reject. What's my conclusion? Well, what does my evidence tell me about correlation or not, though? That's all we really need to say. Insufficient evidence of a correlation. So either you have evidence of a correlation or you don't have evidence of a correlation. That's really all your conclusions are in this case. Even though my R was not 0, it's a little bit of evidence, but it's not enough far away, it's not far enough away from 0 to say there is a correlation. You could also write no evidence of a correlation. Are we okay with the conclusion? There's a follow-up question. What's the follow-up question say? Oh, there's a typo in it.
Does it appear that people with a larger brain are more intelligent?
Does it appear that people with a larger brain are more intelligent? No? Why not? Because there's no correlation. They're saying there's no relationship between brain size and your IQ score. If there's no relationship, we can't say bigger is better or smaller is better or any of that. So the follow-up is no. We don't have a relationship. Between brain size and IQ. Now here's where it gets tricky when we flip over to the corresponding question on 10.2. So this one is on page 149. It's also example 3. So on 149, example 3, it says, here's the brain sizes and IQ scores. Find the regression line. How do I do that?
equals A.
Y equals A plus BX, where the A and the B are on the same screen that gave you your R and your p-value? Yes?
I thought we don't plug it in because there's no correlation.
We don't, but it asked for the line,
Oh, okay.
so you're a step ahead of me. If it asks for the line, we have to write the line. Y equals A plus BX. So off of our calculator, we get 12.45?
51.45.
I couldn't hear you, sorry. Start over.
51.45.
51.45 plus
0.05.
0.05x. We agree with Kirsty's numbers? The A and the B off of our calculator screen? So this is the regression line that they asked us for. Here's where you have to actually think for a moment. Every once in a while I ask you to do that. We just found that there's no evidence of a correlation. Which means that my graph looks like what?
It's all over the
It's
top.
all
It's kind of all over the place. There might be a slight hint of an upswing because of our little bit of an R here. There might be a little bit of a positive if you kind of look back, but not very much. And so this is like the best line they could draw through that data. So imagine, I'm gonna do a rough sketch of it, I don't know that this is it. Imagine that my data looks like that. And so then we got this line, and the line looks like this. It's not really close to much there. I mean, we can put a line through there, but it's not going to be the best prediction because we don't really have a correlation. So just because your calculator can find you this line, doesn't mean it's a good line to use. It'd be if you walk in for a new job and you said, hey, how much are you gonna pay me? And the boss says, that depends. Can you tell me how many Legos you have at your house? I'm gonna plug it in this formula. And then I'll tell you how much you're gonna get paid. And the Legos have nothing to do with your salary, right? So just because I might be able to come up with an equation that relates Legos and salary, I don't think that's how you want them to decide. Unless maybe you have a lot of Legos, it might work to your advantage. But the rest of us, maybe not, because there's no relationship there. So just because you can come up with an equation doesn't mean it's any good. So that's what Hector was asking a minute ago. He thought we weren't going to use it. We're not. We found it, but it's no good. No good. Because we have no correlation. I cannot tell you enough the number of people, it's an R, I don't know why it's a weird R, who will find the line and plug in X every time. That is not how we make the prediction. I need you to flip back over to the bottom of 148 to remind you what I said earlier.
So we're not even gonna bother plugging that number in the number.
We're not going to even bother plugging in that number into here. That's like plugging the Legos in to find out your salary. It's not going to help. Back on the bottom of 148, it said, if there is a correlation, we're going to plug into that line. If there's no linear correlation, what's it say? The best prediction is the mean value of y. So the best prediction in this case is y bar, the mean of the y's. Ooh, how am I going to find it?
You do one bar stack,
I could do one bar stats. With which list?
L1.
L1 is the x's. We gotta do L2, right? Because the y's were in L2. So some options are to do one bar stats with L2. That's one option. What's another way that we could find y bar?
Can't you just do it on the list?
Say that again?
Nothing, no.
Oh, okay, I like you thinking out loud though, that's good. How did you find averages before you met me?
Can't you add them up and just divide?
Yeah, we could add up all the y's and divide by how many we have. Add all y's. Then divide by, how many do we have? Anybody count?
12.
And divide by 12, because there's 12 of them. So these are options. Option 1, Option 2. You have option 3 that you haven't seen before. It's not really much different. You could do 2 var stats. L1 and L2. And it'll tell you what's happening with your x's and with your y's, and you still want to take the y bar off of there. Any of those, I don't care which way you do it, you don't even have to write down how you got it, you just need to tell me you're finding y bar. Yes, ma'am?
Why do we have a triangle?
Because we're trying to make a prediction.
Okay, and then do we do that for both if there's a correlation, if there's no correlation?
No, so go back and read page 148 again when you have a chance. If there's a correlation, we're gonna follow that line because the line tells me there's a relationship. If there's no correlation, then the best thing we can do is take the average. So if you walk in for a new job and you don't want me to make your salary based on how many Legos you have at home, I'm just gonna take the average salary and start you there, because that makes more sense. So the mean is when you don't have a correlation. Any question about the 3 ways of finding your y bar? I'm hoping you found it at least one of these 3 ways. What did we get?
100.08.
100.08? We agree with her? Someone who's not getting that, I need to know so I can help you do
I
it,
see, okay.
whichever method you're doing. I just tend to do Kirsty's first idea, 1 var stats with L2. It's the quickest, easiest, it's more familiar, something we've seen before. The tricky part about this is it calls it X bar. Right, when you do 1 var stats, it calls it X bar, but since you know you were looking at your Y list, that's really your Y bar. So the question was, find the best predicted IQ score for this person whose brain is 1,020 cubic centimeters. I didn't even use that 1,020 at all. Why not? Because there's no correlation, there's no relationship. It's like me using your Legos to figure out your salary. I don't need to know how many Legos you have. And so in this case, we don't care about the size of your brain. We're just going to assume that you have the average brain, the average IQ score. Because your brain size isn't related to it in any way. So this is the best predicted score. Questions? Okay, yes ma'am.
So you say that the conclusions, that's the best predicted score, is that ever gonna change that conclusion of the Y bar?
Are we ever going to do something other than Y bar?
No, like change it, you know how there's no correlation, there is correlation, that's always gonna be the same?
Well, it's either going to be Y bar or Y hat.
Yeah.
It's one or the other, depending on if there's a correlation or not. Okay, so we did all 3 examples in 10.1. There's one more question down here on the bottom of page 149 for 10.2. One more question. It just says find the regression line and the best predicted cost of a ticket purchased 1 day in advance. Given the cost of tickets is $300 if purchased 30 days in advance. So somebody's comparing, I think they're probably plane tickets. If you buy it 30 days ahead versus the day before you leave, looking to see if there's a relationship there at all. This kind of problem will be on your homework, it'll be on your lab, it'll be on your exam. Nowhere here does it ask you to even check to see if there's a correlation. Doesn't even talk about it. Why do we still need to do that?
To see how we can make the line, if we're gonna have a correlation, to use the formula or the Y bar.
Because we need to know that information, she says. We need to know if there's a correlation, because if there's a correlation, we're going to use the line to make our prediction. And if there's not a correlation, we're going to use Y bar like we just did. So you don't even have to write out the formal steps, but you at least have to decide if there's a correlation or not. So how are we going to do that?
Let's get the p-value right.
Get the p-value, that'll help decide. So you put those in there, put them into your calculator. So this is example 4 from 10.2. I would maybe write down my R. And at least a p-value. You got it already, Kevin? What'd you get for R?
OR. 0.709.
Someone agree with him? William's nodding, couple nods, Christian's nodding. What'd you get for a p-value? 0.07?
Mm-hmm.
How can I use that if I didn't write out all these steps? Maybe some of you will still want to because it makes it feel more familiar.
You were assuming alpha's 0.05.
We assume alpha's 0.05 if they didn't give us one.
And then you,
This green pen is not happy today. Alpha equals 0.05.
you test that against the p-value versus the alpha.
P-value compared to our alpha, it's bigger than 0.05. So it would be failed to reject H0, but we didn't bother to write it down. If you didn't write it down, there's two things you could do. Number one is you can go back and write it down. Remember, they're always the same. Or you can look on the top of page 3 there where it tells you what H0 and H1 were. On the top of that table on page 3. Rho equals 0 and rho not equal to 0. So if we didn't reject rho equals 0,
Then there's no correlation.
I have no evidence of a correlation because I'm stuck with rho equals 0. We didn't reject this. Now, technically, I didn't need any of this to enter their, none of this is part of their question, but I needed to do it to be able to decide what to do. No evidence of a correlation. Should I write down my regression line?
Yeah,
Why?
because it asked for it.
Did it?
Find the regression line.
Oh, it did. Okay, thank you. I thought it didn't ask for it. I was going to say, what? If it had just asked for the prediction if I had read the problem, we wouldn't have even had to write the line down. But we can write it down. What is it? Anybody?
Y equals negative 1237.6.
1237.6 plus.
7.07 x.
So there's my regression line. What am I going to do with it? Nothing. Why am I doing nothing with it? Because I got no correlation. So if I want to make a prediction for a $300 ticket 30 days in advance, what am I going to do?
One more step.
One bar stats with
L2.
L2. And we're just going to find the average ticket, the average Y value, which is
690.29.
690.29. The dollar sign. So that's our best estimate. Anytime you're asked to make a prediction, you need to stop and pause and say, do I have a correlation or not? Because if you have a correlation, we're going to actually plug a number into there and figure out my prediction. If I don't have a correlation, I'm going to take the average Y value. Yes?
So like on the test, if it just asks us like this,
Mm-hmm.
does that mean we don't have to write the 5 steps?
Yes.
We still have to.
Mhm. So this problem could be on the test, and I wouldn't have even asked the first part about find the regression line. I could have just given you the data and asked for a prediction, and all you really would have had to do was tell me this. Because that to me tells me that you've already checked for a correlation, you know there isn't, and so that's why I'm taking Y bar. Now, a lot of people will organize their thoughts as they go through it, but technically I just need to either know you're doing this or this. And that's all I need, if that's all I'm asking. That's the tricky part, is the problems in 10.2 don't tell you to test for a correlation, they just ask for predictions, and you know that you need the correlation part to answer it. Yes?
So we only do the regression line if it asks us.
Yes.
So
Or if there's a correlation,
So if there's no correlation and doesn't ask for the regression line.
then you don't need it. It's worthless.
So what do we do?
Then you just do the average Y. Okay, let's talk about part 2 of the project. I have a couple things to give you.